All right, so welcome to part B of week 5. So, what we're going to be doing today is writing equations of polar graphs, and then we're going to talk about systems of polar functions. So, just like any math that we do, we learn how to do it one way and then we go backwards and do it that way. So, we talked about already graphing in polar, given an equation, writing a graph. So, now let's talk about what happens if we're given a graph. What would the equation be? So you can think about this first one being a flower where it's like a one petal rose, or you can think about this better as a circle. So what you have to pay attention to, and we talked about this in previous lessons, is if we're talking about the diameter of this circle, that's actually going to be the coefficient. So when we're writing equations of polar graphs, make sure that it's r equals or theta equals. In this case, it's going to be r equals. Theta equals is usually going to be just a line. So if we have a circle that has a diameter of 6 or the petal length is 6, that's going to be my coefficient. Since this major axis, since it's all on this positive cosine or positive x-axis, it's going to be a positive cosine function. And that's all you have to do. For number 2, it's the same idea where we're going to have a petal length of 1, 2, 3, 4, 5, 6. And this time it's on that negative y-axis. So what we're going to actually do is put a negative 6, and since it's on the y, sine theta. If it was positive 6, it would have been on the positive y-axis, which ends up happening here. So it's petal length 6 or diameter 6 on the positive x-axis, so we have positive 6 sine theta. Then here we have a cardioid. It's not a dimpled limousin because it goes through the pole. So remember that the major axis is always a plus b, and I have that written up here. So this is the major axis here. The minor axis is the one that's going up and down, and that's my length of a. So again, we're writing equations. We're going to put r equals. Well, that a value here is 2. And if you think about, well, if a plus b is equal to 4, and we know that a is 2, what's b? B is also 2. It's going to be plus because we're on the positive x-axis, so it's going to be plus cosine theta. So again, remember that cardioids have a and b that are the exact same. So number 5 over here, it's another cardioid. Notice that the major axis is down here on the negative y-axis. So we're going to have subtraction and we're going to have sine. Well, our a value here, if you count it out, is 2 as well. This a plus b here is 4. So if a is 2, a plus b is equal to 4, then b also has to be 2. Again, we just said that the major axis is the negative y-axis. So it's going to be minus in between a and b and then sine theta. Look at the major axis here. The major axis is over here on the left side. So that's going to be the negative x-axis. And it's going to be another cardioid where the radius is 2, a plus, or not the radius, but this a value is 2, and a plus b is 4. So a and b are both 2 again. And since it's on that negative x-axis, it's minus cosine. Now, this next one is an inner loop limousin, and you don't have to think too much about it. What you need to know is, well, it's r equals. It's on the negative cosine, so it's going to be subtract cosine. A is always that length of the minor axis, so that's going to be 2. And if you think about 1, 2, 3, 4, 5, 6, it's 6 on the major axis. Well, if a plus b equals 6, and we found out that a was 2, then that means b is going to be 4. Well, how is this an inner loop limousin? Well, a is less than b. If you were going to do a minus b to figure out how far you're going on the major axis, you would get -2, which creates that inner loop here of -2. So again, all you really have to think about is the a value on the minor axis, a plus b, and where is your major axis. Number 8 here, this looks like a dimpled limousin, but again, all that is just good to practice on. We get our a value by looking at the length on the minor axis, which is going to be 4. We're on the positive x-axis, so it's going to be plus. And if we count out to here, this is 7. Well, if a plus b is 7 and a is 4, then b has to be 3. And it's cosine theta. So it all kind of works out. Again, if you do the a minus b, you'll end up seeing how that value away from the major axis is at 1. Number 9, inner loop Limoson, where if we are writing an equation, we count the minor axis, which is going to be 3 again. And then it should be 7 going out here. And since we're on the negative x-axis, it's going to be minus. But what do we add to 3 to get to 7? Well, 4 cosine theta. Well, this next one looks almost exactly like that other problem earlier, but we have 1, 2, 3 as our a value, positive, and then we're only going out 1, 2, 3, 4, 5. So that means that what would I add to 3 to get to 5? Well, 2, positive x-axis, so cosine theta. Next one here, again, r equals our minor axis 1, 2, 3, 4, 5. Our a plus b is 1, 2, 3, 4, 5, 6, 7, 8. So we're on the negative y-axis, so it's going to be minus. What do I add to 5 to get to 8? Well, 3, and we're on the y, so sine theta. Well, with flowers, we don't have the plus or minus. What we need to do is kind of like what we did with the diameter of the circle problems here, where we can consider it a one petal rose. Here, we have to take our coefficient as the length of our petal. So it's 1, 2, 3. Now, the question is how do we get sine or cosine? Well, if it's cosine, it starts on the axis. If it starts off of the axis, it's actually sine. And remember that with number of petals, it's different. If n is odd, you get the same number of petals. If n is even, you double that. So since I have 4 petals, I end up putting 2 theta inside of that equation. Because again, if it's even, we double the number of petals. Number 13, we could look to see if it starts on the positive x-axis. You can see here that it starts on the negative sign, but don't think about it that way. Think about, is it starting on this positive x-axis? It is not, so it's going to be a sine graph. So the petal length is 3. We're dealing with sine, and again, if n is even, we double it for the number of petals. This is odd, so we just put 3 theta in there, because if n is odd, you get that same number of petals. Number 14, r equals the length, 1, 2, 3, 4. We're starting on the x-axis, so this is actually cosine. We have 5 petals, which is odd, so 5 theta. Now, number 15 is this vertical line that's tangent to the circle of radius 2. So we could, if we're doing this rectangular wise, we could have it as the equation x equals 2. Well, if we're doing this in polar, x is r cosine, which we can divide both sides by cosine and do 2 over cosine, which doesn't look as well as 2 secant of theta. So make sure that you are writing these without fractions, not that this coefficient can't be a fraction, but that the trig function should not be written as 1 over cosine, but as secant. Look at this one. This is a circle. So is this going to be the same equation like what we did here? Well, no. Notice that the center of these circles were not at the pole. The center of this circle is on the pole. So that means that it's going to be a lot easier to write as in just saying like, oh, well, it's a circle of radius 2, 1, 2. We don't think about this as diameter like we did with these. Again, think of these as one petal roses versus having a circle where the center is at the pole. Well, what about 17 and 18? Well, notice this one leaf rose that's neither on the x or the y axis. It's kind of right in the middle here. Like if you think about the center or this point here being, 45 degrees from here or 45 degrees from here. You can think about it from, the positive x-axis here and go 135 that way or 225 that way. But I'm going to think about it as, okay, starting either at the negative x or the negative sign, how can I rotate it in order to get it to be there? Well, if I start here on this negative x-axis, I'm going to think about this as a negative petal length of 4, 1, 2, 3, 4 on that x-axis, so it's going to be negative 4 cosine. If it was positive 4 cosine, it would have been over here on the right-hand side. Negative 4 is on this side. So if I'm starting here and I'm going counterclockwise 45 degrees, then I'm going to subtract 45 degrees. You could also change that up and say, oh, well, what if I wanted to start here because I like, the y-axis? Well, it was on the negative y, so we're going to do negative 4 sine. And we're actually going to go clockwise in this rotation. If we're doing clockwise, we need to do theta plus 45 degrees. Or if you like radians, put pi over 4. Number 8 here, we're dealing with a tangent line. So you can again think about an equation here that's x equals 4. Or you can think about the equation here that's y equals 4. Well, it's safe to assume, based on this picture, that we're rotating it 45 degrees. We'll make sure that it's very clear on a quiz or anything like that. So if we are going to start off with this x equals 4, well, that's kind of like what we did earlier with our tangent line, that if we had x equals 2, we had 2 secant theta. So I could start off saying that this is 4 secant, but we're rotating that vertical line counterclockwise 45 degrees, so that's going to be a minus 45. If you want to change your perspective and start off with y equals 4, well, that would be 4 cosecant, and we're going in a clockwise rotation, so that's going to be theta plus 45 degrees, knowing which way that you're going. You could also change it up and say, oh, it could have been x equals negative 4 and rotate it 135 degrees. Just pay attention to the directions and make sure that you are providing those correct equations. So anytime we talk about a function, we always kind of want to deal with systems of those functions. In this case, they're not really functions, they're polar graphs, polar equations, but we are able to figure out where they intersect. What's going to be a very important thing to do with polar system of equations is to graph as well as find them algebraically. You have to do both, because sometimes with these polar graphs, you will find points on the graph from graphing them versus those algebraically. So graph these on your own, and then I'll give you a chance to look at what they should look like. So r cosine equals 2. R cosine's x, so x equals 2, so we get that straight vertical line. This 2 plus 4 cosine theta gives us a interleuklimouson that has an a minor axis of 2, a major axis of 6, and then they intersect. So we're going to be looking for the points of intersection here, here, and here. And depending on your graphs, they might look exactly where they need to be. I kind of knew where the points were, so I sketched my graph so that they intersected those points. But sometimes, your graphs aren't perfect, so you need to know exactly where those are, and we're going to do that algebraically. So what I'm going to do for this problem here is do some substitution. We know that r equals 2 plus 4, so I'm going to replace that r with this r by plugging it into there. So I end up getting 2 plus 4 cosine theta times cosine theta equals 2. Well, then I'm going to distribute the cosine and then move the 2 over. So I end up getting 4 cosine squared, and also put it into standard form. 2 cosine theta minus 2 equals 0. Notice that they're all divisible by 2, so I'm going to get 2 cosine squared theta plus cosine theta minus 1. I'm going to factor it. So cosine theta plus 1 and 2 cosine theta minus 1. We set each one equal to 0 and solve for cosine. So cosine theta equals negative 1 and cosine theta equals 1/2. Well, if you inverse cosine both sides, you end up getting that theta equals pi. And we could put plus or minus pi, but we're just going to leave it as a positive one. And then we're going to talk about cosine inverse of 1/2, which is going to be pi over 3 and 5 pi over 3. I'm doing radians here because the graph is in radians and it'll be easier that way. Just pay attention to the directions. Well, just like systems of equations, we end up finding out algebraically what one of the variables is. Well, we need to go and plug it in so that we can figure out what the other variable is. So what I'm going to do is I'm going to pick the easier of the two equations as r cosine theta equals 2 and plug in pi. Oops, I didn't actually plug in pi. Which cosine of pi is negative 1. So you divide both sides by negative 1 and get r is negative 2. So that means I have a point at negative 2 comma pi. Does that make sense? There's no point here on pi. Well, actually there is. If you go pi and negative 2 of a radius, you get that point there. So we're good. If we end up plugging in r cosine of pi over 3, r times cosine pi over 3, you end up getting 4, or equals 2, sorry. And then, so cosine of pi over 3 is 1/2. Divide by sides by 1/2, you get r is 4. Same thing happens if you plug in 5 pi over 3. You end up getting that r is equal to 4. So we'll end up having that point at 4 comma pi over 3. And we'll also have this point here at 4 and 5 pi over 3. Now, does it intersect anywhere else on this graph? No. So those are our 3 points of intersection. How do I know that there's 3? Look at your graphs. You should always graph it and solve it algebraically, because sometimes you might get points that are on the graph that are not algebraic, and then you can check your algebraic by doing the graph. So for this next one, I just already drew both graphs. The 2 plus 4 cosine theta was exactly the same graph that we had previously. And then we have this 2 minus 2 sine theta that has a minor axis of each 2. A plus b is 4. And then it's a cardioid since a and b are the same. So where are these points of intersection? Well, when you plot this, you should realize that, oh, well, both graphs go through that center point. They both have this point here. They both intersect here. Are there any other places? As far as I can see now, no. So let's solve this algebraically. Well, since both equations are r equals, we're going to just set each of the two polar equations equal to each other. Well, if I subtract 2 on both sides, I end up getting negative 2 sine theta equals 4 cosine theta. And if you remember back to what we did with solving equations and identities and stuff like that, what would be the best thing to do here? Well, I could divide both sides by 2 sine theta and get cotangent, but that's not going to be easy to put in or use. So let's actually change it to tangent, and you're going to kind of see why here in a bit. So let's divide both sides by cosine and divide both sides by negative 2. So we end up getting sine theta over cosine theta equals negative 2. Well, sine over cosine is tangent. So where on a unit circle is tangent negative 2? Well, it's not. Our negative 2 is not a part of our unit circle. It's not a unit circle value. So you're going to have to inverse tan both sides. And since our graph is in radians, we're going to stick to the radians. So if you inverse tan negative 2, you get negative 1.07. Well, remember that when we're solving tangent equations, we always need to add or subtract some multiple of pi, depending on where our equation is. So what I'm going to do is we're going to need the calculator to figure out our radius values. So let's grab our calculator. So since we want these kind of angle measures to be positive to make it a little easier to deal with, I'm going to get both of or an angle that's, between 0 and, 6.28. That's, 0 between 0 and 2 pi. So I'm going to add pi to that rainbow value that we got in the calculator. So we're going to talk about theta being 2.034. Again, a positive value to make our angles positive. And if I wanted to get an R value, I can plug it into either one of those two equations. So I'm going to do the 2 minus 2 sine of that and get that my radius value is 0.211. So I get a point that's 0.211, 2.034 radians. Where would that be on our graph here? Well, 2.034 is probably somewhere less than pi, and 0.21 is probably somewhere in here. So there's a point that I found algebraically that I couldn't really see on my graph, but it actually exists. Well, tangent is going to happen twice in this. So what I'm going to do is I'm going to take that value earlier and add pi to that so that I can get the coterminal to negative 1.07. 2.034 is in quadrant 2. Quadrant 4 is the 5.17. So 5.176. And again, if I go in and plug that in to one of the two equations, not inverse sine, I get a radius of 3.789, which, okay, 1, 2, 3. Oh, yeah, that's about that. It's like between 3 and 4. Yeah, there's that point. 5.17 is over here in quadrant 4. So I end up getting that point. Well, wait a minute. There's those 2 points. Again, one of them I found algebraically that I couldn't quite see on my graph. I knew that point, but I know that my graphs are connected here and here. So this is a situation where we get points graphically, but not algebraically. So this point here would be the point 2 comma 0, or you could say negative 2 comma pi, or any one of the ones that you want. But what about this point here? Is this 0, 0? No. Is it 0, 90? Yeah. It's also 0, 0. It's also 0 pi. It's also 0, 3.141, whatever. Any angle that I want is this exact same thing. So there are an infinite number of ways of writing this as an ordered pair. So how do we write our answer for this? Well, we write the pole. So there are 4 answers. How did I know there were 4 answers? Graph it. So make sure you're graphing it and showing all your work in order to solve these systems of polar.